Hello, my name is Priyansh Gadia. I'm a student in the BSc Honours Data Science and Artificial Intelligence online degree program at IIT Guwahati. This video is my submission for Term Project 1. My project is titled as Physiology Grounded Machine Learning for Detecting Flow Termination Transients in Pressure Support Ventilation using Transpulmonary Pressure. This video focuses on phase 2 of what is a 3-phase project. I will start by explaining my problem statement in simple terms. In pressure support ventilation, a breath ends when inspiratory flow falls down to a threshold, not when the timer ends. That switching moment can create a fast pressure transient or a pressure spike. Normal bedside numbers like plateau pressure can't capture these sub-second transients during the active flow, so we have analyzed waveform at a high sampling rate. I shall try to even provide simple definitions throughout my video demonstration and also show my screen where I have uploaded the entire project onto my GitHub repository and try to explain it better. Alright, so I've uploaded the entire project onto my GitHub page, and the repository exists under the name of Respiratory Support Optimization. So I'll quickly show that on the screen as well. So here's my GitHub page, and yeah, you can find all the documentations here, so we don't need to dive too deep. So if you do have any kind of doubts or you're unclear about certain aspects, I've covered everything in detail in various files, and you can even go through the readme, which is like summary of the entire project that we are working on. Moving on, let's discuss about the tools and the dataset. So for the tools, I have used Python mainly, and I use the application VS Code for building this entire project. And the dataset, we have used multiple datasets like the CCVW ICU dataset, the Puritan Bennett dataset, as you can see here. But the main dataset which has helped us throughout this project is the China dataset of the CCVW ICU, because it provided us with all the key signals that we needed for this project, that were airway pressure, the flow, and most importantly the esophageal pressure. Now you can't find esophageal pressure in datasets generally, because it is an invasive method, and you need to have a catheter down your lungs. That's why this kind of data is not easily available. But we have also used the other datasets for cross-verifying and for domain shift analysis and other purposes. So yeah. So let's move on to what we are actually building over here. So we are taking the raw ventilator waveforms and turning them into a clean machine learning dataset, as we have over here, as I've already mentioned, the CCVWICU dataset. So we are cleaning them, and then we are training models to estimate how big a short pressure spike is around the moment when the breath ends. So the main story that we are following is taking the raw signals and extracting features, and training them on a model, and then on its validation. So it's just like any other machine learning pipeline procedure. So the data set I've already talked about, and the target that we are, like, what we are trying to predict. I'll talk about the label that we are using. So the esophageal pressure, as I've already mentioned, it lets us estimate a lung stress proxy, which we call transpulmonary pressure, and we use this transpulmonary pressure spike as size as the label that we want the ML to predict. So this is what our target is. This is what we want to predict, and how we get this transpulmonary pressure. So I'll show you. This is well documented in the documents in the report, and I'll just open this in a new tab, so we can come back to this anytime we want. Over here, the transpulmonary pressure, as I've already mentioned, PL, the lung, it's also called the lung pressure, and this is equal to the airway pressure minus the esophageal pressure. So this is the main label, and this is pretty much the base of our entire project. This is the key equation that we have used over here. Now coming back to the pipeline that we were following. So we first need to turn the raw waveforms into training rows. So this is the data science part. Now if we go back to analysis, and over here in library folder, so the segmentation part, which we'll call this as. So the data that we get from these data set is a long continuous waveform, and we need to convert it into one row per breath. So for each breath, we detect the end of inspiration moment, and we grab a short window around it, and then we measure the spike size. So this is what makes the data set consistent and model ready. So I'll just quickly show the snippet over here. So yes, right over here, as you can see, we are marking the inspiration as a flow, which is above a small epsilon number, and we keep only starts that stay on for a short duration of time. So we do not take noise that create fake breath. So like when we cough, or there's some other jerk or error. So this this part, the find raw rising crosses, that helps us to do that, and we'll move on to the next file, which is the events file. So over here, this particular method. This is a pretty important method. So what this method is doing is it is finding the first we have to find the peak flow in the breath, and then we are setting a threshold. This threshold is ETS into the peak flow. So ETS is basically the end of the breath part that I was talking about. And then we scan forward until the flow stays below that threshold for 3 samples. I'll explain the 3 sample part later. And so this part basically gives that the stable breath ends over here, the timestamp, the exact timestamp of it. And if the window is incomplete or the signals are of low quality, we just skip the breath. We return -1 and say that the cycle is undefined. So yeah, the 3 sample part that I was talking about, you can go over here in config file, and over here see the consecutive sample below the flow of ETS required. So we have set this as 3. Now let's move on to the feature engineering part, the part that we actually are going to give the machine learning model as input. So the features, think of features as a summary number of the waveform shape, like how fast the flow drops, how spiky the pressure is, how much flow area do we see. These features are what the model actually learns from. So over here, yes, this is the file that this is the feature extraction file for the machine learning model. And over here you can see there are a number of excerpts that help us extract feature. So like this one, this line, the slope line, this determines how quickly flow falls during the late inspiration. And below that, the integral of absolute flow. This is like the total magnitude of flow, like area under the curve. And so yeah, so basically we get features like flow deceleration slope, how fast the inhale flow die out, and flow integrals, as I've already said, how much total flow happened in that window. Is pressure smooth or jittery by the spectral ratio as well. So these are the feature part. Now the most important part that I'll say is we have to prevent the model to cheat. So now what happens that some developers, some programmers, they train their machine learning model and they expect a certain output from them, and they train it, and then they see the results and they see that oh, this is not matching to what I had expected. So they'll just quickly go back and then change the parameters and change the thresholds that they have set to just show that yeah, what we have done is successful. But we are not going to do that. We cannot let the model cheat, because again, this is a medical based machine learning project. So this is crucial that we don't submit false responses. So we have used the esophageal pressure to create the label, but we do not give esophageal pressure to the model. Otherwise, the model will look amazing on paper, but it will fail in real life, and that can cause some real consequences. So we keep the inputs restricted to signals typical ventilator has, like airway pressure and flow. So I'll again go back to a file, the local pipeline file, and we also have a global pipeline file. Yes. So over here, the feature columns. So you can find that only flow and airway pressure are allowed, and as the model inputs. Otherwise, they won't be allowed to be given to the model. This is the difference between a research label and a deployable unit. We are trying to make a deployable unit, and this is what I like call the anti-cheating rule. Now moving on to the training and validation part. So how do we train? We have a small data set of only 7 patients, and that's well, that's not enough, but we do not have access to better data sets, so we are working with this one. And the core question is, how can we predict the lung stress spike for a new patient? So to test that honestly, we have used a split called LOPO, which stands for leave one patient out. It means that say we have 7 patients, right? So A to G. So we'll train on patient A to F, and then test on patient G, and then repeat the same cycle for each patient. I'd like to show you the LOPO part which I'm talking about. It's right here in models. So oh yeah, the LOPO splits, as you can see, and all the patient but one is trained on, and then tested patient is the remaining patient. And so basically this split is harder than random split, but it is the one that matters. If we do random split, the model might memorize the patient style, and we don't want that. And the metrics that we get from it, the important result mainly is the mean absolute error, or MA. So that's what we are mainly reporting on. Like it says on average how many centimeters of water, CmH2O is a way of stating the pressure. So how many centimeters of water are we off? So the results. So all these results are actually stored in locally, but I've also reported them in my file, and I'll quickly reproduce them as well later. But over here. So the results are say from logs and plots, and the big key, takeaway is that the signal exists, but generalizing across patient is really hard, because we have just seven data set belongs to data points from 7 patients, and also we show uncertainty to avoid overconfident claims. I'll quickly show you. So as you can see, the primary machine learning models, the XGBoost regressor. We have the benchmark models as well, like the Gaussian process, the ridge regression. So over here, as you can see, the local performance that reports the that uses the LOPO CV, leave one patient out cross validation, and I'm just trying to look for a specific number that I remembered. Okay, so the patient MA comparison, that's this part, but this is the main results that we have derived. The lung pressure, the maximum lung pressure for like the 50th percentile. It means like 50% of breaths are below this value. So, and the 95th percentile as well. So you can see we receive the median pressure of the maximum lung pressure is 99.51 CMSO, and for 95th percentile it's 20.57 CMSO. And for back to the logo CV part, the XGBoost model, we found the MA to be 5.15. Now, important point that the pre-specified gate we were trying to achieve, the target mean absolute error was just 3, but we have observed 5.15, so it has clearly failed. So yeah, a model can look good on one patient and still struggle on the next. That's why we have used LOPO, and we also show the uncertainty bands, as you can see over here, the Gaussian process and the uncertainty carried out on the LOPO CV. Now I'll just quickly demonstrate and show you the logs that I was talking about previously. Alright, so let's quickly finish this by reproducing the findings report. So over here I have my VS Code open, and we'll go to analysis folder and finding reports.py. So when we run this, basically it will produce all the results that we have seen in the final report, and it also generates figures as well. So yeah, so this has been written into the docs file. So as you can see, this has been updated over here right now, and yes, so we have the entire report, and we can see, so the local CV performance is 5.15, and the moving on to the all cohort boundary condition table for that is required for the next phase, the per patient summary. We pretty much have everything over here that we need, all the design envelopes also, that will basically help us in the next the phase 3, the mechanical phase. So yeah, to wrap up, phase 2 has built a data pipeline, created label using the esophageal pressure grounded lung stress estimation. It has trained ML model with an anti-cheating rule, and it has also validated with the local CV split. And this gives us an honest baseline and clear next step for phase 3. So yeah, thank you. That was my project for my first term project. So yeah, thank you.